Hello, and welcome to The Space Above Us, Episode 29, the Apollo Lunar Module. Before we start today, I wanted to make a quick mention of a special anniversary. This podcast is airing on May 4th, 2017, which makes tomorrow, May 5th, 2017, which makes it the 56th anniversary of the flight of Alan Shepard aboard Freedom 7, and the first anniversary of the launch of this podcast. I know this is somewhat cliche, but it's honestly hard for me to believe it's already been a year. I've moved to a new state, started a new job at NASA, and have learned so much about spaceflight history, and have, to my own shock, picked up hundreds of regular listeners. I won't belabor this, but I just wanted to say thanks for listening, and thanks for going along on this ride with me. Last time, we talked about the Apollo Command Module and Service Module. These massive spaceships formed the backbone of each Apollo mission, and were where the crew spent most of their time. Rounding out the three-module mission structure was the subject of today's episode, the Lunar Module. This ungainly machine had an appearance only an engineer could love. It was designed to do one thing, and one thing only: land on the moon and return to lunar orbit. A lot of times when doing research for this show, I learn things that are really difficult for me to wrap my mind around. Things like the amount of fuel used by an F-1 engine, or how many miles of wire were stuffed into an Apollo spacecraft. While researching this episode, there was one fact in particular that really shocked me and didn't really fit into the rest of the episode, so I'm just going to tell you here. When the company that won the bid to build the lunar module, which I can't tell you yet, that'd be a spoiler, was traveling to Houston to finalize the contract with NASA, they called around to some hotels. Before booking their rooms, the company asked if it would be a problem that some of their employees were black. The fact that at a time when humanity was making plans to depart the Earth for the moon, that this was a question that needed to be asked really blew my mind. What's even crazier is the hotel said yes, it was a problem, but that they could use the back entrance and be brought some food from the kitchen. The company said they'd look elsewhere. It just goes to show you that technological and social progress don't necessarily move in lockstep. Wow. While North American aviation was hard at work on the primary Apollo spacecraft, NASA had yet to decide how to actually fly to the moon. And at what I hope at this point is old news, the critical question of mode needed to be decided. When the decision to embrace lunar orbit rendezvous was announced in July of 1962, a whole new spacecraft that nobody expected suddenly joined our story, the Lunar Module. The Lunar Module, or LEM as it was quickly shortened to, was an unusual vehicle in almost every aspect. While thoughts on specialized lunar landing vehicles had been kicking around aerospace studies for years, the contract for its construction was even more nebulous than the command and service modules. No one knew how to land on the moon, including NASA. Whoever won the privilege of building this vehicle would have to work with NASA to figure it out on the fly. So here's the deal. NASA wants someone to build a vehicle to land on the moon and return to lunar orbit. They didn't know what it should look like, what it should be made out of, the properties of what they'll be landing on, what the environment it would fly through would be like, or the best way to control it. Anyone interested? It turns out a lot of companies were interested, most especially North American Aviation. Despite having their plate overflowing with the Command Module, Service Module, and S-2 rocket stage, North American wanted their chance at the prestige of building the moon landing vehicle. Up until this point, it was assumed that that would be, the Apollo spacecraft. With this new spacecraft arriving out of nowhere and leaving them spinning in circles above the moon, North American wanted it all. Thankfully for the overall moon landing effort, NASA intervened and forbade North American from submitting a proposal. Not that I think they couldn't do it, I just think that doing all of the above may have been a bit much for any one company to handle. After a lengthy bidding process, the company that emerged victorious was not North American, but rather Grumman Aircraft, headquartered in Bethpage, New York, on Long Island. Grumman had yet to land a major contract from NASA, but not from lack of trying. They had bid on Project Mercury, as well as the main Apollo spacecraft. The studies they performed in Lunar Orbit Rendezvous, without NASA funding, also contributed to its eventual selection. Without realizing it at the time, Their early work on the mode problem eventually led to their enviable assignment of designing the first vehicle to land humans on another world. Similar to North American, Grumman's usual projects were military aircraft, especially for the Navy. Their contributions to the war effort during World War II included the Wildcat fighter and the Avenger bomber, among many others. This next project was going to be a little less focused on aerodynamics. The lunar module is made up of two main parts, the ascent stage and the descent stage. Put together, the whole thing is 23 feet high, with the deployed footpads making up a 31 foot by 31 foot square, which, if you take a moment to think about it, is pretty insane. It's actually roughly as big as the house I lived in during high school. As you may be able to guess, the descent stage is used for the actual landing, while the ascent stage is used for returning from the surface. Let's take a look at the descent stage first. If you were to remove the shiny golden insulation and peel back the skin of the descent stage, you would find that the main structure was a cruciform, which is a fancy word for the shape made by a plus sign. The ends of the plus sign were connected with flat paneling, creating a sort of octagon shape. Inside the octagon, you would find 5 square compartments and 4 compartments that were squares cut in half diagonally. The large square compartments around the edges contained propellant tanks, while the center compartment contained the rocket engine used for the descent. Arranged around the outside of this structure was the landing gear. The original designs for the LEM featured an immobile landing gear, which is great because it's simple, but as weight demands grew, they were forced to switch to a deployable gear system. When the LEM was packed away in the space between the top of the S4B third stage and the bottom of the service module engine bell, it had its legs pulled inward in order to fit inside the adapter. The 4 points connecting the LEM landing gear with the walls of the spacecraft adapter were the only mechanisms holding the LEM in place during launch. Once the LEM was in space, they could pop the landing legs out, where they would stay forever. They were not retractable. Mounted to the forward leg of the landing gear was a ladder for the crew to easily climb down to and back up from the lunar surface. That's better than the original plan, which involved a bunch of ropes and tackle and block. It's crazy. On top of the ladder was a small flat platform that led into the hatch to the ascent stage. Naturally, the platform was soon called the front porch. At the base of each landing leg was a large footpad nearly 3 feet in diameter. The footpads were so wide because no one was really sure how stable the lunar surface would be. Maybe it would just be a bunch of squishy dust. So they opted to make the landing surface as wide as possible. Beneath 3 of the footpads were 5.5-foot long probes that would alert the crew to an imminent landing. When they touched the surface, a contact indicator would light up in the cabin, letting the crew know that it was time to brace themselves and get ready to turn off the engine. One of the coolest features of the lunar module landing gear was how it dealt with the impact forces of the landing itself. Typical landing gear, in something like a passenger jet, would use hydraulic shock absorbers. The technology is well understood, and it can withstand a large number of impacts before it needs to be replaced. The flip side of this is that hydraulic landing gear is relatively complicated and, worse, heavy. The solution was a classic example of engineers taking the unique details of a situation and exploiting them as much as possible. Hydraulic landing gear is a natural choice for an airplane because an airplane is going to land thousands and thousands of times. The LEM only needed to land once, so there was no need to use a shock absorbing system that was reusable. Instead of heavy hydraulic shock absorbers, the LEM landing gear contained specialized cylinders made out of aluminum in a honeycomb arrangement. When the LEM landed on the surface of the moon, the legs would crush these honeycomb cores at a predictable rate, spreading the impact forces out over time. Of course, once crushed, the core couldn't be uncrushed, and that was just fine as far as Apollo was concerned. One interesting side note on crushable cores. A similar technology is used today in the landing legs of the far larger Falcon 9 first stage, made by SpaceX. If the booster lands perfectly, the cores are left intact. But if the Falcon sets down a little harder than planned, the cores are there to pick up the slack, ensuring that the relatively cheap crush cores are all that need to be replaced, rather than the entire rocket. This is also why the booster used to launch TICOM 8 had a distinct lean after landing. One of the legs had to make use of its crush core. The rocket engine used in the descent stage was unusual in that it needed to be capable of running at a wide power range. Throttling a rocket engine is tricky since it's already nearly impossible to get a rocket engine to work properly under ideal circumstances. Changing the thrust level on the fly had the potential to introduce all sorts of problems like the dreaded combustion instability. The engine for the descent stage, imaginatively named the Descent Propulsion System, was capable of throttling back to as low as 10% of its maximum thrust. The propulsion engineers probably could have taken some tips from their buddies over at North American, since the X-15 featured the first large-scale throttleable rocket engine. Maybe they did. I didn't actually run that one down. In order to compensate for complicated requirements like deep engine throttle, the DPS was kept as simple as possible in other areas. It used a pintle injector to get the propellants into the combustion chamber. This is a gross oversimplification, but a typical rocket engine injector plate could be compared to a shower head, whereas a pintle injector could be compared to that thing in a garden hose nozzle that controls how wide the spray pattern is. Additionally, rather than tricky regenerative cooling techniques used in other engines, the DPS relied on the nice, simple ablative cooling strategy to ensure that the engine survived the trip to the surface. But as simple as it was, the descent propulsion system was nothing compared to the simplicity of the ascent propulsion system perched right above it. Nestled into the center of the ascent stage's underbelly, the APS was simplicity itself. It could not be gimbaled, steered, or throttled. The propellants were forced into the combustion chamber by a simple pressure-driven system, no complicated turbopumps in sight. And the propellants themselves, similar to those of the DPS, were hypergolic, which meant that there was no need for a complicated ignition system. Just bring the two hypergolic compounds together, and they'll ignite themselves. Why such a dumbed-down system? Reliability. The ascent propulsion system absolutely, positively had to work 100% of the time. Every other propulsion system used in Apollo had a number of options for recovering the astronauts safely if they failed. Saturn V? Just fire up the launch escape tower and plunk down in the ocean. Third stage fails to send you on your way to the moon? No problem, just head on back to Earth. Service propulsion system won't turn on and inject you into lunar orbit? Well, we sent you on a free return trajectory for a reason. See you in a few days. And if the descent propulsion system failed to light, well, that's a bummer that we came all this way, but at least you can enjoy the view before you turn around and head back to the command module. The ascent propulsion system was different. The only time it would be fired was when the astronauts had already landed on the surface of the moon. If it didn't work, there were no options. Full stop. So it better work. First time, every time. Surrounding the ascent propulsion system was the ascent stage itself. This strange, lumpy structure was an engineering marvel. Its job was to keep the astronauts safe during their stay on the moon, and then return them from the surface to the orbiting command module above. Every aspect of its bizarre appearance was dictated by engineering necessity. When every gram matters, there's no room for cosmetics. When looking at the ascent stage, one of the first things that jumps out at you is the fact that it's asymmetrical. This was because the two large propellant tanks, one for fuel, one for oxidizer, had different weights. In order to maintain the center of gravity, the fuel tank is perched further off to the side, giving the vehicle a puffy cheek appearance. On the top of the ascent stage is a hole that looks like it has an inverted cone stuffed into it. That's the docking port for the command module. The docking is made with a bunch of beefy latches in order to maintain a pressurized connection between the two vehicles while still being able to disconnect and reconnect again later. Also on top of the ascent stage were a number of antennae for communication with the Earth and CSM, as well as a radar used for rendezvous with the CSM. Spaced evenly around the ascent stage were 4 clusters of reaction control thrusters, which were used to point the LEM in the proper direction. These were positioned such that each quad was placed in between the landing legs below, so that the plumes wouldn't impinge on the legs, heating them up and causing all sorts of damage. Nevertheless, scoop-like plume deflectors were added beneath the RCS on all LEMs after Apollo 9. In the center of the front face of the ascent stage is the square hatch. Like everything else in the LEM, it is the way it is because it had to be. The original round hatch was too hard to get through with a big rectangular backpack. The hatch was round at first since it was originally going to also be a docking port, allowing the LEM crew to see where they were going when docking with the command module. But having a docking port on the front as well as the top added a lot of weight, and it turned out that adding a small window directly above the commander's position in the LEM made redocking on the top a possibility. That left Grumman engineers free to remove the docking port from the front, along with the reinforcement necessary to withstand the gentle but significant docking forces, as well as make the round hatch square. On either side of the hatch are two triangular windows that give the LEM a sort of worried appearance. Each window leans slightly outward to give the lunar module pilot and commander a clear view of the terrain beneath them. The windows are smaller than you might expect, especially compared to the LEM's closest earthbound analog, the helicopter. But the LEM engineers had a trick up their sleeves. The original LEM design proposal actually did feature large helicopter-like windows. But these were super heavy and made it difficult to protect against micrometeoroids or maintain a consistent temperature. They seemed necessary though, since how else would the crew be able to get a good view from their seats? Well, who said they needed seats? During landing, the forces from the descent engine would only be about 1 G, just like standing on the Earth. The landing itself was expected to be pretty gentle, and hey, human legs are pretty great shock absorbers. With a little Velcro to stick their feet on the floor, and some tensioned lanyards to hold them into place, the crew could do just fine without seats. Once Grumman engineers realized the crew could stand up during landing, the window problem solved itself. With the crew standing right next to the front face of the vehicle, the window could be a lot smaller and still provide a wide field of view. It also meant that the crew's knees wouldn't be banging up against the console and that the entire cabin could actually be made slightly shorter, saving still more precious weight. It's amazing what an impact one good outside-the-box idea can have. Surrounding the crew was a similar bewilderment of switches, lights, controls, and indicators as in the command module. In fact, in many cases they were identical. In an effort to reduce the already staggering amount of training required by the crew, similar interfaces were used in the LEM wherever possible. The commander and LMP each had their own identical sets of controls for the reaction control system and main engine. The right hand controlled attitude, the direction they were facing, using a traditional flight stick hand controller. The left hand controlled both translation, moving side to side in any direction, as well as the throttle for the main engine, though in practice the computer handled the engine throttle on its own for the most part. The left-hand control was a sort of T-bar that could be bumped up and down, side to side, or in and out, depending on what movement was desired. One of my favorite features of the LEM, just for how clever it is, are the indicator lines painted on the windows. We'll be getting into the details of landing in a few episodes, but the LEM was actually capable of automated landing on the surface. The computer would try to land on a preset patch of terrain, but the position could be updated by the astronaut, moving it uprange, downrange, or side to side. To do this, the astronauts would need a way to know where they were telling the computer to go. They accomplished this by using these indicators on the windows, called the landing point designators. The two axes of the indicators formed a kind of grid overlay on the lunar surface. But here's the problem. If the crew were to position their heads anywhere not along a precise line, the indicator would not line up with the ground as expected. Here's the clever bit. The landing point designators were on the inside and outside panes of the windows. In order to use them, a crew member simply had to position his head such that the two sets of lines were precisely on top of each other. If he did that, he was properly aligned and could use the landing point designator to tell the computer where to land. Of course, these guys being test pilots and all, every last one of them took over manual control instead of letting the computer land because of course they did. But that's a story for another day. Taking our attention away from the windows and control panels and inspecting the rest of the ascent module interior, we find a number of storage compartments and utilities for stuff like filling up the spacesuit backpacks. Directly behind the crew positions is a strange little cylindrical table protruding into the cabin. This was actually the top of the ascent propulsion system engine. Space is a little tight on these vehicles. During their stay on the surface, and a temporary return to gravity, the crew could catch some shut-eye in a pair of hammocks that would be hung from the sides of the cabin. Something about sleeping in a hammock on the surface of the moon is just the coolest thing. The Apollo Lunar Module was surely a strange beast. With no margin for cosmetics or nice-to-haves, it was a bare-bones utilitarian oddity, with each component crafted by necessity. In total, 10 would fly in space, with all but one of them supporting a human crew. And notably, one even served as a trusty lifeboat for the crew of Apollo 13. The LEM was like nothing that flew before, and nothing will ever be quite like it. And with that, our Apollo Prologue series is over. We talked about the origins of the program, the ground infrastructure that allowed it to happen, the monstrous rockets and engines that powered it, the intricate computers that guided it, and the command, service, and lunar modules that actually flew the missions. The goal of this prologue wasn't necessarily to end it with each and every one of you becoming an expert in all of these diverse subject matters, but rather I wanted to make sure I laid some good groundwork for what could be used as a foundation for the missions to come. Each Apollo mission is incredibly complex and unique in its own way. With this foundation firmly underfoot, it should allow us to spend more time on the fascinating details of each individual mission. Next time, we will be moving on to the Apollo flights themselves. But as fate would have it, we will begin with tragedy. The first flight of the Apollo program never flew at all. During a routine test on the launch pad, the spacecraft and its crew were lost in a flash. The events of Apollo 1 shocked the nation and rocked the nascent space program to its core. So join us in 2 weeks as we remember the brave crew of Apollo 1 and try to learn from their sacrifice. Ad Astra. Catch you on the next pass.